So the empty set, AKA the null set, is a set that has nothing in it. It's exactly what it sounds like if you were to say empty set. You can use, this is the symbol you'll want to use here, the kind of like the Ghostbusters symbol. And that's what you want to use. We're in section 2.1. 2.1. So this is where they're trying to trip you up here. They're asking which of these is the empty set. Well, this is a set, but it contains the element 0 in it, which means it's not empty. There's something in this set. So no, that's not the empty set. This is just the number 0 standing by itself. There's no set involved here, so it's not the empty set. So it's a little bit confusing. The number 0 is a number representing nothingness. The empty set is a special construct called a set, and it is a set that has nothing in it. It is not a number itself, but it's a similar idea. There's an analogy that can be drawn there. Which of the following is the empty set? All x such that x is a number less than 4 or greater than 10. Well, it's not saying number less than 4 and greater than 10. It's saying one or the other. So are there numbers less than 4? You bet. There's an infinite amount of numbers less than 4. So all those numbers are in this set. Are there numbers greater than 10? You bet. There's an infinite amount of them. All of those are in this set. So is this set empty? Absolutely not. There's tons and tons of things in this set. But this one, all x such that x is a square with 3 sides. Are there any squares with 3 sides? Is that the definition of a square? Absolutely not. So is there anything in that set? No. So it is the empty set, yes. So it sounds simple, but we need the empty set just like we need the number 0 when you're talking about numbers. It's a necessary evil, if you will. So set membership. This is a symbol that we're about to introduce that can tell us if something is an element of a set. It looks like an E or like a sideways trident. What it means is an element of. So when I use this symbol, I'm saying this is an element of this set. When I cross through the symbol, when I say use the E, but then I slash through it, let me see if I can zoom in on that. I slash through it, I'm saying it's not an element of. I'm saying this is not an element of. It is a symbol that shows up all the time in mathematics. And again, you don't have to write this down explicitly. You just tell yourself that symbol, the elongated E, means is an element of. So let's determine if the following are true or false, but let's make it fun and not give away things. Bad, bad, bad. So pretend you didn't see the answers already. Wipe your mind, put on your mental windshield wipers. I know we all have them. We probably needed them on the drive this morning. Let's determine whether the following are true or false. The lowercase letter r is an element of the set A, B, C, ... all the way to Z. True, absolutely. Very good. Now, we didn't explicitly write out every letter of the alphabet here, but we established a clear pattern and then we used ellipses points to say what that pattern was, and then it goes on until it gets to Z. So just because it's not explicitly written doesn't mean we haven't symbolized that it's in there. How about this next one? True or false? 7 is not an element of the set containing 1, 2, 3, 4, 5. Yeah, absolutely. And that one's confusing because we're saying true that it's not, but that is exactly what's going on here. Now, this next one is meant to cook your noodle a little bit. It's meant to confuse you. The set containing A is an element of the set containing A and B. I'll just come out and tell you that's going to be false. And the reason it's false is because this is so confusing, and I hate it when they go to this level. But the idea is that the set containing A is a set. It's not an element, or it's not a single element. If I were to have done this, then that's a true statement, because now you're saying the element A by itself with no set brackets, A is an element of this set. Suddenly that becomes a true statement. But that's not what I've done. I've put set brackets around it, which means it itself is its own new object. It's the set containing A, and it is not an element of this set. It is very weird. It is weird, I'll give you that, but it is kind of exactly what's going on here. What we're going to see, though, is it is a subset. We're going to define something called a subset later. Sure. Right, exactly, because then you're saying the opposite, and then it suddenly becomes true. Exactly. In fact, that's a good way to think about things when we get to chapter 3 and logic. We'll talk about negations and how the negation of a true statement is false and vice versa. Good thinking. Now we're going to talk about a very super uber duper important set in mathematics called the natural numbers, or the set of natural numbers. They use this script n here. They use this script n. Really, that should be written like this. Like that. And so what it is it's the set of all numbers starting at 1, and it goes on to infinity, but it's just whole numbers, positive whole numbers. The ellipses points say that this goes on forever and ever and ever. So the natural numbers are just all the positive whole numbers. What is the largest natural number? What's that? Exactly. It doesn't have one, does it? There is no largest natural number. If I got $3 trillion in my bank account, which I don't, but if I did, well, there's always 3 trillion and 1, isn't there? No matter how large a number you can think of, you can always go one more than that. You can always keep adding to it. So there is no largest natural number. There is, however, a smallest natural number, which of course is the number 1. So no largest natural number. But now remember, we're talking about this as a set. So let's play around with this. Give me a second. So let's express each of the following sets using the roster method, which, remember, the roster method is where you list out the elements explicitly, or maybe use an ellipses point. Set A is the set of all natural numbers less than 5. Now, if I just said the set of numbers less than 5, there's an infinite amount of them, because I could go into negative numbers. I could go into parts of numbers like 1.5, 1.56, 2.3748921, something like that. By imposing natural, by saying it has to be natural, I've suddenly given myself a much smaller amount of choices, haven't I? And so now, let's zoom in. Well, now all my things are gone. But now by doing that, that can only be the first four whole numbers, 1, 2, 3, 4. And that's it. So the word natural automatically imposes restrictions that could make something infinitely large into very small and finite amount of things. Set B is the set of natural numbers greater than or equal to 25. Okay, they got to be natural. They got to be greater than or equal to 25. So if I write them in order, I would start with 25, greater than or equal to. I can go to 26. I can go to 27. Is there a largest one? No. Yeah, it keeps going. So I'm just going to use ellipses points. And there you go. So this is an infinite set. There are an infinite amount of things in it. But even though it's infinite, there's still some restrictions on it. It can't just be anything you want. All x such that x is an element of the naturals and x is even. In other words, all even natural numbers. Right. So it'll be, they're calling it E, all the even numbers, basically, starting with 2, 4, 6, 8. Does it keep going? It does. It goes on forever, never stops. So all I wanted us to do is to list these things out in roster notation. So just a quick remembrance, quick guide. Remember what your less than symbol means. Remember what your less than or equal to symbol means. Remember what your greater than symbol means and what your greater than or equal to symbol means. I'm going to assume that's something you already know. So just keep in mind, if they impose this restriction that you must be talking about natural numbers, that automatically restricts what you can use. All natural numbers less than 4, there's only 1, 2, 3. That's it. All natural numbers less than or equal to 4, you can now throw the 4 in, but there's still only a finite amount of them. All natural numbers greater than 4, well, can't include 4, but then you can go 5, 6, 7, 8, 9, 10, and that goes on forever. You can even have two-way inequalities or inequalities that have two things involved. All natural numbers greater than 4 and less than 8. So you can't include the 4 or the 8. So that would just be the numbers 5, 6, 7. They got to be natural. So you can't have any weird fraction numbers. You can't have 5.5. Can't have 5.89. None of that business. Here's a little trick question for you. What if we said all natural numbers greater than 4, but less than 5? What would it be? Well, it's got to be also less than 5. So all natural numbers basically greater than 4, but less than 5. Would there be any? No, there wouldn't be any natural numbers. If you could do real numbers, you could do 4.6, you could do 4.1, 4.02. But since they have to be natural, there's nothing that is greater than 4, but less than 5. No such number. So this would actually be, not that, it would be the empty set. So they could throw a little trickery onto you like that. And don't believe for 1 second that they won't, because they will. This one, all natural numbers greater than or equal to 4, but less than or equal to 8. So you can include the 4 and the 8 there. And then you can do mixed things like this, less than or equal to here, but a strict less than means you can't use the 8 here. Here you can't use the 4 because it's strictly greater than 4, but less than or equal to 8. Again, if I played with it a little bit, just for fun, and I changed all of those to 5s. 5, go here, give me 1 second. 5, 5. So now these are all natural numbers greater than or equal to 4, less than or equal to 5. Earlier, it was the empty set because I was not allowed to include 4 or 5 themselves, but here I can. So suddenly, that becomes this set, and it's allowed. Suddenly it becomes the set containing both 4 and 5. On this next one, you got to be greater than or equal to 4, but less than 5. So you can at least include the 4, but you're not allowed to include the 5 in that case. It's got to be less than. And it's got to be natural. So you can't do 4.6, 4.7. That's not going to happen. And then over here, what would this set look like down here? Just 5, exactly. Just the set containing 5. Yep. So for something that's pretty simple, like the positive whole numbers, you can start to get real tricky with it, and you can start to make it a lot less simple than it really looks. So if you want to express each of the following sets using the roster method, remember roster methods where you basically list them out as much as you can. This set is all x such that x is a natural number and x is less than or equal to 100. Well, it's not going to be infinitely large because it's bounded from above. So you can go all the way as low as 1, and then you can count your way up to 100. Count your way up to 100. That's what this set would look like. All natural numbers less than or equal to 100. All natural numbers greater than or equal to 70, but less than 100. You can go as low as 70. You can include the 70, but you work your way up. You can get to 99, and then you got to stop because you can't go to 100. Does that make sense? Pretty straightforward. Good stuff. Now, in this next slide, they're going to introduce a word that sounds way harder than it really is. What we're going to be doing next, we are going to want to count up the number of things that are in a set. We're going to want to have some way of saying there's 4 elements in that set, there's 27 elements in that set, there's an infinite number of elements in that set. The natural numbers have an infinite number of elements in them because they can keep going and going and going and going. The word they use is cardinality, or the cardinal number. Why do they use that word? It's just a word, it's just a definition. They decided it works. That's what they want to call it. The cardinal number of a set A is just the number of elements in that set. You're just counting, basically. Now, counting can be tricky. I promise you that. Counting can be a lot trickier than you think. It's easy to count something that only has 5 to 10, 20 things in it. But there's almost 2.6 million 5-card hands you could get in poker. You're not going to count those by hand. You're going to have to use some kind of mathematical formulas, which we will cover later on in chapter 11. That's way later. So the cardinal number, they use this symbol, N of A. They say the number of things in A. That's just a shorthand way of saying we're talking about the cardinal number of things in A. So don't let the cardinal number, the idea of it, throw you off. Let's look at this first set. The set A here is the set containing the numbers 7, 9, 11, and 13. Without even looking at the PowerPoint, which immediately gives away the answer, how many things are in there? How many elements are in A? 4. You've got, it doesn't matter that the numbers are not 1, 2, 3, 4. You've got 1, 2, 3, 4 things in there. So the number of things in A is 4. Let's even block these off a little bit. So all we're doing when we're talking about cardinality, we are talking about the number of things in that set. This set B here, this set B, is the set containing the number 0. Is it the empty set? No, it's got something in it, doesn't it? Just because what it has in it is the number representing nothingness, that is still something. That element itself still exists. How many things are in this set? Just 1, exactly. Next up, set C. We're going to have to do a little bit of counting. It's all the natural numbers between 13 and 23, including 13 and 23. There's no better way, in my opinion, than to just count them out. 13, 4. How many of you are tempted to say there's 10 things in there? How many of you are tempted to say there's 10 things? You'd be off because you want to say, oh, just do 23 minus 13, which is 10, and you're done. But let's count it out together, and you're going to see you're wrong, and I'll explain why. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. There's actually 11 things in that set. I mean, just counting it out, you can see there's 11 things. Do you guys want to know why? Yeah, exactly. What happens when you're doing subtraction? When you're doing subtraction, you're not counting the endpoints themselves. You're counting the number of spaces in between the numbers. And this will just be a fun little side thing. This is a common mistake. Think about the numbers 13, 14, and 15. If I do 15 minus 13, I only get 2 because all I'm doing when you do subtraction, 15 minus 13, you're actually just counting the number of spaces. There's 1, 2 spaces there. 2 spaces. So subtraction just counts the gaps in between the numbers. It doesn't count the numbers themselves. There's going to be one more than you're thinking always. It's just like if you read pages 113 to 120 in your book. You think you're only reading 7 pages because 120 minus 113 is 7. But again, you're only counting the space in between those numbers. You're not counting the numbers themselves. There's always going to be one more than you think. That is a mistake that is very easy to make. So be careful. Exactly. In fact, that's sometimes called the n+1 rule. Yeah. You always add 1 back onto it to account for that extra thing you didn't count, the first number. Yeah, that is exactly right. So fun stuff. Now, we're going to learn a definition for sets that is going to sound so wrong that you almost don't want to believe it, but it's going to be true. When we're talking about sets, when I use the word equivalent, all I care about is, do they have the same number of elements? So let's read the definition carefully. Set A is equivalent to set B if they contain the same number of elements. So this set here that has the letters B, G, and I. As contrary as you might think, this set is equivalent to the set containing the numbers 14, 27, and 39. How many of you that blows your mind? You're like, what? The word equivalent, though, it's just a definition at the end of the day. If you talk about numbers, equivalent means they're the same number. But if you're talking about sets, you're saying they have the same number of things in them, not that they are the exact same set. That's confusing, I'll give you that. And that's why sometimes I don't even cover this definition, because to me, who cares? Who cares about saying they're equivalent? It's not going to be something that comes up a lot, but it's just a definition. So equivalency is just an issue of how many elements does each set have. Give me 1 second, please. There's a student trying to get in here. Okay. So equivalent just means they have the same number of elements. So looking at these two sets, A is all X such that X is a vowel. In other words, it's the set of all the vowels, A, E, I, O, U. Y is not a vowel, as tempting as it is to make it one. And then this other set, all natural numbers greater than or equal to 3, but less than or equal to 7. That means it has 3, 4, 5, 6, 7 in it. It's got 5 things in it. These both have 5 things, so they are said to be equivalent. Again, that's not something you normally would think, but it is true. The word you want, when two sets are exactly the same, not only do they have the same a number of elements, they have the same actual elements themselves. We call that equal. We call that equal. I'm not worried about that. There it is. So two sets are equal if they are the exact same set. Now we might rearrange the objects in the set. They don't have to be in the same order. They don't have to be in the same order. But they have to have the exact same elements. A quick side note. Repetitions are not necessary in a set. In other words, you don't need multiples of the same element. If you got the number 3 in your set, you're golden. You've already said there's a 3 in there. You can use that 3 as many times as you want for whatever your purpose is. So you only need to represent that value one time. So when there are repetitions in a set, throw out the repeats. You do not need to have this. The set containing 1, if you see this, you see the number 2 is in there multiple times. You see the number 3 is in there multiple times. We don't include them multiple times. So this is really just the set 1, 2, 3, 4. Excuse me. So put another way, repeats are not allowed. They're not necessary. You can throw out any repeats. You just need one representative for that group of values or elements. So keep that in mind. Thus, these two sets here are actually equal. They're equal because they have the same exact elements, and any repeats are ignored. You completely ignore them. Throw them out. They're not necessary. So our next definition, we've already kind of danced around it, so we won't spend too horribly much time. Again, some of these definitions are very, very, very detailed. The difference between a finite set and an infinite set. And yes, I almost just fell over, but I have very good balance. I caught myself at the last second, so I would never live that down. If I fell over, you would never see me again. I would leave the room and that would be it. No, that's not true. I would just get myself up, and if you laugh at me, you'd hurt my feelings very seriously. My feelings would just be broken beyond repair, and you would never see me again. That's not true. Anyways, humor, humor, humor. Yes, I am capable of humor despite talking about mathematics. Okay, so finite versus infinite sets, it's exactly what you think. This definition is going to be very, very complicated. An infinite set is a set that has an infinite number of elements in it. It is not a set which includes the infinity symbol. That is still, that one's kind of tricky. But it's just got an infinite number of things in it. The natural numbers is an infinite set because it goes 1, 2, 3, 4, 5, and then it keeps going, 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 going. It never stops. A finite set has a finite number of elements in it. It either has 0 elements or it's a number that is not infinity. 5, 6, 3,456,291,327,054. Even though that's a huge number, that is still a finite number. So it's exactly what it sounds like. A finite set has a finite number of elements in it. So this is a confusing definition. Don't let it trip you up. So some very simple true false here. The set containing the elements 4, 8, and 9 is equal to the set containing the elements 8, 9, and 4. What do y'all think? True or false? And don't look at my hand. That's not possibly going to be able to cover it. How many of you would say true on that? It's true, not just because it says it already. It's true because the ordering of things in a set don't matter. You've got a set with 4, 8, and 9 in it. Another set with 8, 9, and 4. They're the exact same thing. Exactly. It's got to be the exact same set, even if you rearrange them. Exactly. This one down here, this is the set 1, 3, 5. Now this set has 1, 3, 5 in it, but because it's got an extra friend in there, suddenly these are not the same set anymore. They're very similar, but they're not the same. What we're about to study here in like literally the next PowerPoint I open, the next section, we're going to learn that this is a subset of that, but they're not equal. Okay, so let me pull up our next section concerning subsets. Did she give you the right notes? Did she put them? Are they? I sent her a zip file that had all the notes I'm using in it. That's weird. Okay, I'll double check what I sent her. But it was just that. Oh, that is college algebra. That's math 13, 14. What's that? Yeah. Okay. Do you want me to email her? Or yeah, I'll just see if maybe she had a different class in mind or something. Okay, yeah, so that would be, those would be your college algebra notes. Okay, so the next thing we're going to talk about are subsets. It's kind of going to be what you're thinking. When you think of a subset, think of a large pool of objects, and then just pick a few of them out of there and form a new set out of that. You've created a subset. And that's pretty much a good intuition for what this means. A subset is just a smaller set that you've pulled from the larger set. You can't add new things that weren't already found in the larger set. Otherwise, you're not talking about a subset anymore. So we learn a new symbol. Set A is a subset of set B, expressed like this. I'll write it a little larger for you because I'm just a nice guy. It is not the less than or equal to symbol. It looks like a horseshoe or a magnet on its side, a nice elongated C with a line underneath it. So make sure you don't put any sharpness. It's a nice curved shape. Set A is a subset of set B if every element in set A is also found in set B. Wait a minute, doesn't that mean they're equal? No, it's just saying set A, think of it as the smaller set, if you will, from a larger pool. Whatever set A is, whatever its elements are, those elements must also be found in set B, but set B is allowed to have more elements than just those. It's just that set A you can take everything from set B and form set A out of it. But set B could be larger. It's actually possible that they are equal using this definition, but we'll see that distinction in just a moment. If you use this notation where you cross through it, it's just like saying is not a subset of. It's just like that element of, not element of. It's just like saying equal to, not equal to. It just depends on how you want to use it. So there's a really weird implication here. Every set is a subset of itself. Whoa, that's kind of silly. Let's look at this. Let's look at this in detail. And by the way, real quick, is everyone doing good out there in the Zoomosphere? Can you hear me, Major Tom? Are you doing good? Let me know if you are. Send me a thumbs up or a smiley face. All good. Thank you, Zane. Let's see here. Let's say we have the set containing the elements Texas, and Wyoming. Texas and Wyoming. And let's say we're supposing this is a subset of all X such that X is a US state. True or false? What do you guys think? The set containing Texas and Wyoming is a subset of all US states, the set containing all US states. True? Absolutely, it's true. Yes, true. The reason is that this set here, every element of this set is also found in this potentially larger set. We only pulled from this larger set, basically. All right. Now, Let's mix it up a little bit. Let's mix it up. Let's say we have the set containing the elements Texas, Wyoming, and Dallas. I was going to put Weatherford, but it wouldn't fit there. So I picked Dallas. Is this still a true statement? No. Is Dallas a U.S. state? No. So every element of this cannot be found in this larger set. So now it's false. Very good. So subset simply means you take a small grouping from a larger set, but you can't add something new into your new small group that you created. You can't add something that was out of bounds. So now this is a false statement. Very good. Let me think of something else that's clever. Where's my clear? There it is. Something else that's clever. How about all X such that X is a U.S. state that begins with the letter T. Is that a subset of this set? True or false? This one's tricky, isn't it? X is a state that begins with the letter T. What are all the states that begin with T? Yeah. Are there any? I'm actually asking this for real. There's no others, right? I didn't forget any. There's no tiny state, tiny California. No, there's not. So no, there's only those two states, right? So is this, even though it sounds like it's a nice big set, it's really not. The only two elements in this are Texas and Tennessee, aren't they? So is this a subset of that? It is. True. Because every element in this first set can be found in this other set. How many of you see a problem there, though? Or maybe you see a potential issue. What's the issue? Aren't they the exact same set? They're the exact same set. This is the set containing Texas and Tennessee. This is the set containing Texas and Tennessee, isn't it? They're exactly identical, aren't they? There are two expressions or two different ways of expressing the same thing. So here's a hint. They may be identical, but one is still a subset of the other by the strict definition of subset. That's the key here. The word subset, it doesn't mean necessarily, even though you see the prefix sub, just because you see that doesn't mean that the subset has to be smaller than the larger set. That may not be true at all. They could be the exact same set. So by definition, every set, I don't care what set you want to give me, every set is automatically a subset of itself, simply because it fits that very loose subset definition. So don't let the word or the prefix, don't let sub throw you off. Sub makes you think smaller, diminutive, but don't let that throw you off. It will usually mean smaller, but not always. Okay, so let's look at a few of these things. Let me fix things a little bit. No. Okay, so in this activity, it's a very simple one. We're going to write the is a subset of, or is not a subset of. We're going to cross through it to make true statements out of the following. So here's the set A. It's got the elements 1, 3, 5, 7 in it. The first 4 odd numbers. Here's the set B. It's got 1, 3, 5, 7, 9, and 11 as well. Would you say that set A is a subset of B? Yeah, absolutely. Everything here in A can also be found in B. It also happens to be the good kind of subset where it is truly smaller than the larger set, which is usually how we like it. But remember, even if they were the exact same, it would still be true. So yes, we can put this symbol here and be perfectly happy with it. Now, here, this is just bad. The set A is the set all x such that x is a letter in the word proof. So the set A is really just the letters P, R, O, F. You don't need 2 O's in there. The set B, all y such that y is a letter in the word roof. So the set B is just the letters R, O, and F. Is set A a subset of B? No, because set A is actually larger than B. If it's larger, even if they have some similar elements, if it's larger, it's definitely not going to be a subset. So we would use this symbol. We would write the subset symbol and say, no, cross right through. If I went the other way around, is B a subset of A? It is actually, yeah, it will be, because A is the letters P, R, O, F. B is the letters R, O, F. So then B would have taken all of its values from A, if you will. So if I went the other way around, that's true. If I go the other way around. But just the way it was written there, it's not true. Okay, so I just got done preaching to you, if you will. Almost fell again. I just got done preaching to you about how a subset doesn't necessarily mean smaller than. But now, that's how we would naturally think of a subset. You see the word, the prefix sub, you think smaller. Well, now you get to have your day. A proper subset is what you're thinking. A is a proper subset of B if A is a subset of B and they're not equal and they are not the same set. That means A truly must be smaller than the set B. And all of A's elements come from B, which is what you really think of when you see the word subset. So that's why they stick the word proper into it, because then that makes it sound correct. It makes it, it's like it reconciles this problem. So A is a proper subset of B, which you write using this symbol. It's like the curved part, the horseshoe, without a line underneath it. You write it like that, like a sideways capital U. If the two sets are not the same and A is truly a subset of B. Now, this is what you think of. This is what you normally want when you think of the word subset. Notice how we had this symbol for just regular subset. Doesn't that kind of look like the less than or equal to symbol? Kind of reminds you of that? That's good, because it kind of is like that. The word subset means it has to be smaller or it could be equal to it. And that's exactly a great analogy. Doesn't this just kind of look like the regular less than sign? Well, now it is. For a proper subset, set A truly has to be smaller than set B. So thinking of it like the less than sign, strictly less than, is not a bad analogy. It's actually really on point. It's why we use those symbols. All right. So we are going to, in this activity, we're going to write either the is a subset symbol, or we're going to write is a proper subset symbol, or we're going to write neither. So let me delete a few things here, go away. So let's say we have the set A. A is basically the set of all people living in San Francisco right now, living in San Francisco. B is the set of all people living in California. Is San Francisco a city in California? Yes. So would you say that A is a subset of B? That all people living in San Francisco is a subset of all people living in California? Yeah, I would say so. If you live in San Francisco, you live in California because you are inherently from California if you're from San Francisco. So this symbol, the is a subset symbol, checks out here. Would you even go the extra mile and say it's a proper subset? Yeah. This symbol also checks out because the set of all people living in San Francisco is clearly a subset of the set of all people living in California, and it's strictly smaller than the set of people living in California. Because California also has Los Angeles and San Diego and plenty of other cities and towns and whatnot. So both of these are true. You could use either one and you would be right. This is the better one to use though because it's more explicit. Next example, the set A is the set of numbers 2, 4, 6, 8. Who do we appreciate? Can't believe I said that. I apologize. Sometimes, things take over. 2, 4, 6, 8. Is that a subset of the set 2, 8, 4, 6? That's kind of a weird one. So let's think about the definition of subset. A subset, all elements of A here must also be found in B. So look, A has a 2, B has a 2. A has a 4, B has a 4. A has a 6, B has a 6. A has an 8, B has an 8. So would you say that A is a subset of B? Yeah. In fact, they're equal, aren't they? So I can use my subset symbol here and I'm accurate. Is it a proper subset? No. For it to be proper, it has to be a subset of B and have less total elements than B, which it doesn't. So I can't use that symbol because they are in fact equal. Think of it like this. If two sets are equal, they are subsets of each other. That sounds silly. It's true by definition, but that sounds like we're almost exploiting a cheat, right? Or we're tricking the rule or something like that. So what a proper subset does is it plugs that hole. It says, no, you can't use that little cheat. To be a proper subset, you got to be a subset and you got to be smaller than it, like you would think the word sub implies. So it's silly, kind of a little bit of a confusing distinction, but it is true nonetheless. Now, here's one that's really going to cook your noodle. The empty set is a subset of every other set. Hold the phone there, Pilgrim. The set containing nothing in it. The empty set is a subset of any other set, including itself. The empty set is a subset of itself. Why? We're talking about such silly distinctions. Why is that the case? Well, think about this example here. The set containing the elements 1 and 2. The set containing the elements 1, 2, 3, 4. Clearly, this is a subset of this. This is a subset of this, you can tell, because all the elements from here are found in here. This is true because all the elements of the first set are also found in the second set. Fair enough. Alternatively, another way of saying that, there are no elements in the first set that can't also be found in the second set. Wouldn't you agree that that's the same thing? It sounds like we're playing with the words a little bit, and we kind of are, but it's true. If everything in set A can be found in set B, that means there's nothing in set A that can't also be found in set B. It's like we're using a double negative. In fact, that's exactly what we're doing. So now, think about the empty set. The empty set has nothing in it. See that cold, empty space staring back at you from afar. This first way of thinking about subsets here doesn't really help you to make that understanding, but the second way does. There are no elements in this set that can't also be found in this set, right? It fits this second way of thinking about it. It's silly because there's nothing even in here that could fail the test, which is why it passes the test. So this is like when you walk in and you get a free 100 on something, even though you didn't do anything. You just automatically pass the test because you didn't fail it. It's silly, but it works. Thus, the empty set is a subset of the set containing 1, 2, 3, 4, because of this second formulation of the same idea. It's a bit confusing, but it is true. And then to add insult to injury, the empty set is a proper subset of anything that has at least one element. So again, a little bit silly, but it is true. Okay, stay around. We're going to take attendance real quick. Don't leave. Don't leave.